Thank you. Thank you for the award, and thank you for inviting me to present some of our research. So the topic of the talk is going to be about new advances in satellite-based exposure modeling, lessons learned from models in the US, Mexico, Israel, and Europe. Before I dive into that, I want to quickly present the lab, the Environmental Exposure Assessment Lab at BGU, where we focus on the challenges of developing robust, high-resolution environmental exposure assessment models and studying unbiased exposure health outcome associations in environmental health studies. We apply advanced geostatistical methods and novel GIS and remote sensing-based technologies to address these scientific challenges. We study, among other things, PM2.5, PM10, air pollution hybrid satellite-based models, air temperature exposure assessment models, NO2 land use regression-based modeling, light at night satellite-based exposure modeling, and these are all based on these hybrid methodologies based on Earth observations. We also study and develop built environment models such as walkability indexes, SES exposures, greenness analysis. We of course use all these products in environmental epidemiology study. I also co-lead another lab, the Mobile Measurement and Spatial Modeling Lab at BGU, where we focus on developing, validating, and developing applications of new mobile technologies such as environmental sensors, wearable devices, and geospatial platforms for continuous collection of environmental data. We develop, validate, and deploy robust low-cost sensors. The Green Campus initiative is gonna see some of these sensors deployed in the next few weeks. We look at developing novel methods to overcome self-sampling biases and do location-based social network analysis where we download textual and image data and process that. So having said that, let's discuss what is satellite-based modeling and why do we need it. Why do we actually model air pollution, specifically PM2.5, NO2, PM10, and temperature? We know that there's extensive literature on the PM2.5 associations with health outcomes, which include hospital admissions, mortality, reduced birth weights, cardiovascular disease, particulate matter smaller than 2.5 diameter, air pollution particles, and heart attacks. And we've published quite extensively on this topic in recent years. Just as these associations with air pollution have been published, in recent years we're looking at associations with climate change in health. And changes in climate will lead to warmer temperature and more extreme weather events, which are associated with increased morbidity and mortality, specifically in sensitive populations. So women giving birth, elderly populations. And it's important to say that this increase doesn't only happen during heat events, but also during less extreme events. So what have we been using to assess exposure as exposure scientists? There's several model types: proximity-based measurements, assigning the closest exposure from a close road or a monitor station, statistical interpolation methods using modern networks, land use regression methodologies, which are still quite common today, line dispersion models. But recently, our group and a lot of other groups are looking at hybrid methodologies. Why are we doing that? Because past models have severe limitation. They tend to be clustered around cities. They are using large geographical areas, such as statewide or nationwide analysis, and they potentially bias the health effect risk estimate due to exposure measurement error or exposure bias. And again, these monitors are usually clustered in urban areas. For example, in Israel, most of the monitors are clustered in Tel Aviv and Haifa. And the bulk of the population also live in these urban areas. So to overcome these limitations, we started exploring about 10 years ago using hybrid methodologies incorporating satellite data. The broad spatial coverage of satellites allows us to expand exposure data beyond the range of conventional ground monitoring networks to penetrate both rural and suburban areas. This greatly enhances our ability to estimate subject-specific exposure at the residence level. These measurements, collected daily with fine resolution, allows us to robustly reconstruct backwards, both spatially and temporally, these patterns of exposure. Some of the advantages and disadvantages of satellite data: again, the broad spatial coverage, surveying areas with very limited ground access. They're very economic. We just need one sensor for the entire globe. But it comes with a lot of disadvantages. There's issues with data availability. If there's a snowstorm or a dust storm, if it's nighttime, if there's clouds covering the area, we don't have access to data. There's no vertical profile. We're interested in what people are exposed on the ground level. And the satellite provides the whole column of air, which poses challenges. And we're talking about very different spatial and temporal scales from the satellites. To overcome these challenges, we started developing hybrid models. The first model that we started developing is a air pollution model, a high resolution PM model. And we're using mainly the moderate resolution imaging spectroradiometer, the MODIS platform, which consists of two satellites, the Terra satellite, launched in 1999, and the Aqua satellite, launched in 2002. These instruments provide data in 36 spectral bands, varying spatial and temporal resolution, but among the main products that we use is AOD, aerosol optical depth, and LST, land surface temperature. This is an example of the product coming from NASA. There's different algorithms, some more equipped to deal with darker surfaces such as oceans, some equipped to deal with lighter surfaces such as desert in Israel. But we have a long-standing collaboration with the MAYAC project led by Alexei Liapustin, the PI. And the advantage of MAYAC is that it performs well both over light and dark surfaces and has a much higher native spatial resolution of 1 kilometer. So aerosol optical depth or aerosol optical thickness measures the light extinction by aerosol scattering and its absorption in the atmospheric column. It's a unitless value where lower numbers denote cleaner days. For example, an AOD value of 0.02 means a very clean day, and higher levels resulting in more polluted regions or days. And we developed a methodology to use these satellite images, processing them through our geospatial software packages. This is an example of a day of AOD over the Northeast. You can see warmer colors corresponding to higher levels of AOD in the area. We developed a series of geospatial algorithms to link the satellite data that changes both spatially and temporally to the other monitor data, which is static, and other spatial temporal predictors. Remember, we're trying to calibrate and get information on the breathable or ground level exposure. So we add additional spatial and temporal predictors into the model, linking everything together into a geospatial database. And in very simplistic terms, because it's quite more complex, we have a few steps in the model trying to simplify. The first step is the calibration stage, where when we regress the ground data, in this case PM 2.5 versus the satellite data and additional spatial temporal predictor. Once we have this calibration set, we can go on to areas that we don't have satellite data, but we don't have monitor data, but we do have satellite data and predict there. And finally, because we're interested in environmental epidemiology application, we want to predict for every point for every day. We have a series of sophisticated interpolations that borrow information from across space and time and predicts daily at every point, even when satellite data is unavailable. We then added the local stage, which is a high resolution prediction at a 100-meter resolution using machine learning methodologies, and I'll go a bit deeper into the methodology later. So we developed these models around 10 years ago. We have a very robust model and framework. We have a lot of collaboration resulting in more than 150 publications to date using our models. And this is an example of one of the earliest predictions that we developed over the Northeast. This is an example of daily PM 2.5 predictions across the Boston area. You can see the spatial variability in the city. You can see the difference between the rural and urban area, and even the mall capturing the roads going out of Boston. And this is the local stage, the high resolution exposure predictions across the Boston area. Model performance was excellent with overall cross-validated rigorous R-squared testing of 0.88 and slopes close to 1, showing very minimal bias in our modeling. So as much as we have fun as exposure scientists developing these models and running these new algorithms, we want to use this in an applicative way, and this is an example of how we use this. This is a study looking at short-term effects of particle exposures on hospital admissions in the Mid-Atlantic. In 2014, we published it in PLOS One. We know that many studies report significant associations between PM 2.5 and hospital admissions. These studies rely mostly on a very limited numbers of monitors, and thus we have issues with generalizability and potential selection bias. Using a spatio-temporally resolved model like ours, we can investigate both the short-term effect, because we predict daily, and long-term effect of exposures on hospital admissions in the elderly population in the Mid-Atlantic using Medicare data. This is an example of what happens if you don't have a model, right? You can have population clusters in big cities. The monitors are denoted by these the black flags, and you can assign exposure to each of the population living within 30 kilometers of the monitor station. Even 30 kilometers is quite coarse, and we know these days that introduces a lot of exposure misclassification. So a lot of the population, again, is excluded. By applying a spatio-temporally resolved model, you can include the whole population and assess exposure at a very high level at the residents daily across the whole time period. This is the result of an epidemiology study that we conducted, a case crossover analysis for each admission type, matching on day of the week, month, and year, and defined the hazard period of lag 0.1, that is the moving average of the day of admission exposure and the previous day. And as you can see, we find significant positive association with exposure to air pollution and increase in all respiratory, cardiovascular, stroke, COPD, and IHD admissions. So that's great. We developed a model. Satellites are global, right? We cover the whole globe. We thought, that's very easy. Let's deploy everything across the globe. We'll be done with it in a few weeks, and we'll have a global model. Not so fast, because unfortunately there isn't a one-size-fits-all solution. We see that in every region that we try to expand, we see very different geoclimatic characteristics, including unique challenges. For example, in Mexico City, where we have a cohort running, we have issues with humidity and precipitation, a very low planetary boundary layer that affects the particles like a pressure cooker effect. We have strong wind regimes. In Israel, completely different issues. We have very bright surfaces. We had to go back and forth with our collaborators in NASA to fine-tune the AOD algorithm to account for that. We have issues with sandstorms. How do you differentiate between non-anthropogenic particles and anthropogenic particles? And in general, much higher levels of PM levels. So in each country that we deploy these models, we had to dramatically change the model and develop a new model. In Israel, we had to develop a dust classification method to deal with the issues of dust storms. In Mexico, again, taking into account elevation gradients and humidity. So each area had to account for a different model. And now moving forward to recent innovations in exposure modeling. So the first thing is looking intradaily. So far we've managed to predict daily predictions. What happens if you want to go intradaily? So we wanted to estimate PM10 and PM2.5 in Israel, both for the 24-hour mean, but also hourly for the Terra and the Aqua overpasses. The hypothesis was that in the morning time, when the planetary boundary layer is higher, there's a much more anthropogenic activity. The particles would be very different than in the afternoon when the Aqua satellite overpasses. The P-bill goes higher, a lot of long-range transported particles are coming in, and thus we can maybe use them as two different exposures within a health outcome model. So we used a three-stage hybrid mixed modeling approach, and the main findings were that indeed we found significant differences in concentrations of PM relative to the mean daily concentrations between the morning and the afternoon exposures. We also saw different spatial patterns on the mean PM for non-dust periods days, that is days that are not affected by dust storms. And also we saw that we can use this new exposure as anthropogenic and background or non-anthropogenic exposures as two different exposure in health outcome models quite successfully. Again, model performance was very good across the different models. We see here a model of the PM10, a map of the PM10 concentrations across Israel and the PM2.5 concentrations, and you can see the different spatial patterns of the hourly data compared to the 24-hour mean. Another interesting approach we took was dealing with the computational efficiency and the performance of the model away from urban areas. We apply the Gaussian Markov random field approach to do this. GRF is a common statistical approach for analysis of spatiotemporal dependency over continuous domains, but it's very computationally inefficient. If you want to run it across an area such as the continental US, you can't really do it with the hardware these days. What we did to overcome this approach was approximating GRF with a Markov approach. The Markov property induces conditional independence between random variables, and thus a data point in GMRF depends only on its space-time neighbors, greatly enhancing computational efficiency. This is an example of our old models using linear mixed effect models versus the GMRF model. You can see that the GMRF on the top has a continuous spatial random effects that are smoother over space compared to the slab structure of the old LMM models. In addition, you can see that in this graph on the right here, the farther away that you go away from monitors in urban areas, the GMRF actually outperforms the LMM model dramatically, which is great for performance in rural areas. Another example of our enhancement or improvement that we're seeking is over large areas. If we want to model a continent or continental France, we have issues. We have a large population, 80% of them living in urban areas, and 30% of the city greater than 500,000, and we want to monitor the whole continent. The first challenge of doing this is sparse monitor data. For example, in France, if you look at the PM2.5 distribution, spatial distribution, you can see that we have a lack of monitors covering the whole continent. So the first thing that we have to develop was an algorithm to impute PM2.5 stations based on existing data from PM10 stations that are co-located in the same area, which greatly enhanced our capability to get monitor data continuously. Second challenge was AOD data. As I mentioned, a lot of the time we don't have AOD data for various reasons: cloud coverage, snow, and you can see the frequency of AOD observations across France for 2012. We can see we have a lot of missingness across several regions. We developed a machine learning approach using gradient boosting and random forest to fill in AOD based on CAM's atmospheric reanalysis, and thus imputing full surfaces of satellite AOD even before we start with the calibration stage. The third challenge is indeed, how do we generate robust predictions over an area that's very varied in terms of the geoclimate conditions and the distribution of particles. So we employed a new methodology using ensemble methods to basically fuse in together three different models. We started with our classic linear mixed effect model, a GMRF model that we've developed, and a random forest approach, and ran each of these models separately across the whole chain. So we get different prediction for the LMM, GMRF, and random forest. And as you can see, model performance was already quite good. Each model has its own biases. Each model has different performance metrics. And these are the maps that we generated for each of the specific models. On the left, you can see the mean for the linear mixed model, GMRF, and random forest approach. By ensembling the different models, we allow the predictions to move freely over both space and time, resulting in an overall better performance. So what we do in essence is we impute the PM data, we impute the satellite data, robustly validate that, we run the full chain for each model, so gradient boosting, LMM, random forest, GMRF, and we get an estimation. We then use a GAM framework to ensemble the prediction to get an overall better improvement in PM estimation across different regions. Again, each model has its own biases, and this is a result of this ensembling approach. You can look at the performance of the GAM model outperforming the different discrete models. You can see also the lower RMSE or RMSPE, the prediction error. And again, looking at the annual prediction error, you can see how the GAM really outperforms each discrete model. Now moving over to something else, temperature model. We know that we need temperature for epidemiological study because if we don't have any spatial variation, there's going to be exposure measurement error and thus inducing bias. As we know, weather stations are rarely dense enough in rural areas. And we know that reanalysis data or global climate models are very computationally inefficient and also don't always go into deeper, high resolution, sub 1 kilometer resolution. So what we did is, again, apply some of our developed approaches, but also pushed it forward by using machine learning and big data methodologies. This is an example of one of our first models in 2015, I think, or 2014, sorry, over New York City. You can see the differences in spatial variation between the downtown area of New York, and the outskirts of the rural areas in New York. And you can clearly see Central Park, and you can see the variation of 1 to 2 degree aggregated over the whole time period. And of course, if you look at extreme events, you can have even a greater variation. Again, model performance was very good in terms of the model runs. And of course, reviewers kind of threw us into different directions, trying to validate spatially, temporally, between rural and urban. And model performance was always very, very good. We have applied some of these methodologies in Israel and in France. I won't go too much into that because I want to present some of the new stuff that we're doing. One of the things is going deeper in terms of resolution. So we're not talking about 1 kilometer, but sub-resolutions of 200 meters. This is an example of the model that we ran in France recently. So we have a daily model that goes into 1 kilometer spatial resolution. But then we have a dynamic shifting model that goes deeper in terms of resolution in urban areas. Our hypothesis was that in urban areas, we expect much more intra-urban variation as opposed to rural areas where elevation depending, you don't expect a lot of spatial variability. And thus the model downshifts into 200 meters in 103 French cities. So we applied a similar approach, calibrating, this time using a random forest approach between the satellite data, which is land surface temperature, and the monitor data. We then predict a full grid using the relationship and using interpolations to borrow information across space. And finally, we apply a local stage, taking the residuals and running 2 separate models, a gradient boosting model and a machine learning model, to get at high resolution predictions in cities. This is an ensemble. This time we're using a tensor product, which smooths over latitude and longitude, which provides daily 200 meter predictions and 1 kilometer predictions across France for a 20-year period. These are the results. You can see the prediction maps across France and also the high resolution predictions. You can see the different higher resolution predictions, which allows us to get at greater spatial variability across urban areas. Performance, again, was also great. And finally, moving towards hourly data. So far, we went further in terms of the spatial resolution. How about going further in terms of the temporal resolution? This is a work that we did recently in Israel, where we looked at imputing land surface temperature first from MODIS and SVERI satellites, and then generating these hourly 1 kilometer predictions. We used several satellites here, MODIS satellite, the SVERI satellite, and reanalysis global data. This is an example on the left of the ECMWF reanalysis data, and on the right, the SVERI data, which is a geostationary satellite that has a coarser temporal, spatial resolution, but a higher temporal resolution. So in the first stage of imputation, we use a random forest approach to impute and create full surfaces of the MODIS land surface temperature data hourly. This is an example of a 9 a.m. prediction for a specific day, where we have the MODIS original data, and on the right, the imputed data. So we cover and create these full surfaces. Finally, in terms of the prediction quality, we're talking about very rigorous validation, and we have an RMSE of 0.65, showing very good predictive power. Finally, we took the data that we imputed into a random forest regression analysis, and we're able to create these hourly temperature prediction, again, at a high resolution across 20 years in Israel, again, with excellent model performance of 1.58 root mean square prediction error. And I know I don't have much more time, so I just want to, 1 more minute? Okay, so sorry. So just quickly present some other things that we do in the lab. We have noise estimation models. We have an Apple California official grant we were awarded last year, looking at validating environmental sensor using Apple Watches and mobile devices, looking at comparing results from noise sensors from an Apple Watch to gold level standard devices, and develop an application to collect environmental data in real time. We're building these COTS sensors, deploying them using mobile campaigns, and deploying them in meshes. We do light and night studies, greenness studies, and I'll stop at that. And I want to thank, of course, my BGU colleagues, my colleagues internationally, and last but not least, of course, my amazing past and present students, which without them, this work would definitely not be possible. So thank you very much, everyone.